مرحبا. Okay, we've seen in the previous session what is a matrix, and we defined when two matrices are equal, and we defined how do we add two matrices to obtain a third matrix. Okay, now in this session we want to introduce another operation on matrices, which is multiplication of matrices, but it's not a very straightforward operation, or it's not easy. It's not as straightforward to define as addition. So let's try to explain it. So the beginning is that we have two matrices. So we have matrices A and B. We have matrix A, whose entries are denoted by Aij, and this matrix is of dimension m by k, which means we have m rows and k columns. And we have another matrix B, whose entries are denoted by Bij. Remember, what is Bij? It's the entry in the matrix B which lies in the ith row and the jth column. And this B is of dimension k by n. Okay, so notice here that the first condition in order to be able to define multiplication is to have the number of columns of A to be equal to the number of rows of B. Okay. Then we want to define the multiplication of A and B to be a matrix. Let's call it C, and C is the multiplication of A times B, and let's denote the entry of this new matrix by Cij. And I am telling you that this matrix will be of dimension m by n. Okay, it remains to tell you what is Cij, what is the entry in C in the ith row and jth column. Okay, so where Cij is equal, but before I tell you, I want to explain it in a diagram. So let me suppose this is the matrix. So this is the matrix A. Okay, we will multiply it with the matrix B. Okay, so this is the matrix A multiplied by the matrix B, and we want from this multiplication to obtain a matrix C. Okay, where A has dimension m by k and B has dimension k by n, and C, we will see it will have dimension m by n. And I want to tell you what is the entry Cij. So what is Cij? It is say this entry Cij. It's the entry which lies in the ith row. Okay, so this is the ith row of C and jth column. Okay, so this is the jth column. So how do you find this entry in the product C, which is A times B? You need two ingredients to compute Cij. You need, again, let me tell you what is the slogan for multiplication is row by column, by which I mean to find Cij, you look at the ith row of A. So here you go to the ith row of A. So this is the ith row of A, and by column means the jth column of B. So here you go to B and you look at the jth column. Okay, so this is the jth column. Okay, and what do you know about what do you know about these two, this row and this column, that they are of the same length? Here we have k entries, and in this jth column we also have k entries. So what these entries are called? This is the ith row, so this is AI1 and then AI2, and when do we stop? Until the last one, but which is, we have k columns here, so this is AIK. This is the kth column in A. Now if we look at the entries here, what are the entries here? The first one, so this is B, first row 1, and which column? This is the J, so this will be B1J, and then second row B2J, and then B3J until the last one. What is the last one? It will be at the kth row, so this will be BKJ. So see, here we have k elements and here we have k elements. What do? We multiply them, so we multiply the corresponding numbers. So we multiply AI1 with B1J, and then we add it to the product of AI2 with B2J, and then we add it to the next one until we keep summing the products until the last one, which is the last entry in the ith row of A times the last entry in the jth column of B. Okay, so let me write this. So and then the number you get is Cij. So we need to do all of this just to get one entry in Cij, which is, the entry Cij. Okay, so let me tell you now what is the formula for Cij. So this is what is this? This is the jth column. Okay, now from this picture, what is Cij? Cij, it is AI1 times B1J plus AI2 times B2J plus and so on until the last entry in the ith row of A, which is AIK times the last entry in the jth column of B, which is BKJ. Okay, so this is the definition of multiplication. Okay, so this is how you compute the ith entry and the entry in the ith row and jth column of the product C using the ith row, using what? The ith row of A and the jth column of B. So let me write this again using the sigma notation. So AB is the matrix whose entries are Cij, where what is Cij? Cij is the summation where L ranges from 1 to K of AIL BLJ. Okay, maybe to see this, look. So look here, we are using the sigma notation to represent these summations, and what we are summing, these are the terms we are summing. And look, what is the form of every term? It is of the form I, look, I is fixed here, and then we have the counter L, where L ranges from 1 and then 2 up to and stops at K. So AIL BLJ, and this counter L ranges from 1 up to K. So that's why this is the ijth entry in the product. This is the formula for the product. Okay, maybe it's complicated with this formula. Let's do an example to get a clear picture. So now, example. Suppose A is the matrix 1, 0, 4, and then 2, 1, 1, and then 3, 1, 0, and the final row is 0, 2, 2. Okay, so this is the matrix A, and now we have another matrix B, and the matrix B is the matrix whose first row is 2, 4, and the second is 1, 1, and then the third is 3, 0. So here is the matrix B. Let's first check if we can multiply them. What is the dimension of this one? Okay, it's 4 rows times 3 columns. So this is 4 times 3, and this has 3 rows and 2 columns. So this is 3 by 2. since the number of columns of the first one is equal to the number of rows of the second one, then we can multiply, and we expect the product to be of dimension 4 by 2. Okay, so C, which is equal to A times B, will have 4 rows and 2 columns. Okay. Now let's, for example, we don't need to compute all of them. If you want just one entry, say the entry C32. So what's C32? It's this entry, C32. It's in the third row and the second column. So how do you compute C32 from A and B? Again, the slogan is row by column. So what do? Is you go to the third row of A. So 1, 2, 3. So you look at the third row of A. And 2 means the second column of B. You look at the second column of B, you see that these 2 row and column have the same number of entries. You multiply them and add. You multiply the corresponding entries and add. So this means that C32 is equal to 3 times 4. So 3 times 4 plus 1 times 1, which is 1, plus 0 times 0, which is 0, and this number is 13. 12 plus 1 is 13, so we know that here we have the number 13. Okay, now if you want to get this number, what is this number? This is C in the first row, second column. Okay, so what's C12? So you look at the first row and second column again. So 1 times 4 is 4, plus 0 times 1 is 0, plus 4 times 0 is 0. So this is 4 plus 0 is 4. And so we know that this entry is 4. So you keep doing this, and until you get all the entries, check that this is the product. And so see that this matrix has dimension 4 by 2. We have 4 rows and 2 columns. Okay. If you want to check how did we get this 2, then what is this 2? It's C1, 2, 3, 4, 4, 2. So look at the fourth column. I will use green now. Of A and the second column of B, and multiply the corresponding entries and add them. 0 times 4 is 0, 2 plus 1 is 2, plus 2 times 0 is 0, so we get 0 plus 2 plus 0, which is 2. Okay, check. Anyway, now note that B times A is undefined. Why B times A is undefined in this example? Because look, what is the dimension of B? It's 3 by 2, right? B has dimension 3 by 2. And what is the dimension of A? It is 4 by 3. A has dimension 4 by 3, and these two numbers are not equal. We need them to be equal in order to define multiplication. Okay, let's have another example on multiplication. So suppose A is the 2 by 2 matrix, 1, 1, 2, 1, and B is another square matrix, 2 by 2 matrix, 2, 1, 1, 1. Okay, now let's compute AB. Okay, to get the first entry, you look at the first row and the first row of A and the first column of B. So 1 times 2 is 2, plus 1, we get 3 here. You keep doing this and you get 2 and then 5 and then 3. Okay, so how do we get 5? This is the entry. Okay, so what is this entry? It's in the second. Okay, let me call it C. The entries here are C in the second row and first. So you look at the second in A times the first column, second row in A times the first column in B. 2 times 2 is 4, plus 1 times 1 is 1, 4 times 1 is 5. Okay, so you get 5 here. Now, the moral of this example, or the story of the lesson of this example, is let's compute b times a. We can compute it here, it's defined. But how do you compute b times a? So first you look at the first row in b times the first column in a. So 2 times 1 is 2, plus 1 times 2 is 2, 2 plus 2 is 4. And then to compute this one, you look at, okay, so what is, let's call the entry here D. D, first row, second column. So I look at the first row of B. So look at this first row of B times second column of A and multiply them. 2 times 1 is 2, plus 1, we get 3 here. In the same way, we get this to be 3 and this to be 2. So what do you conclude from this example is that AB is not equal to BA, simply because this entry is 3 and its corresponding entry in this matrix is 4. So this means that, so moral of the story, that matrix multiplication in general is not commutative, okay, because we found an example for two matrices in which A times B is not equal to B times A. Okay. Now let's introduce another important matrix in matrices called the identity matrix. So the identity matrix. So what is this identity matrix? It's a square matrix of dimension n. So let's denote it by in, and let's say its entry is denoted by delta ij. Okay, where, what is delta ij? This is a real number. It is 1. It's a piecewise definition. Delta ij is 1 if I is equal to j. So I is equal to j means that the entry lies on the main diagonal and 0 otherwise. Okay, so all what I'm saying, and it's okay, of dimension n by n. Okay, this in. So what's I1? It's the identity matrix of dimension 1 by 1, so it has only one entry, and it has, which is 1, because 1 is equal to 1. Okay. Now what's I2? This is the 2 by 2 matrix whose main diagonal is 1. All the entries on the main diagonal is 1 and 0 otherwise. Okay, see here, what is this? This is delta 1 1, this is delta 2 2. So I'm saying when I is equal to j, then you put 1, otherwise you put 0. Okay, let's see what is I3. This is the matrix of 3 by 3, of dimension 3 by 3, in which the main diagonal is 1 and all other entries are zeros. Okay. So these are the identity matrices. So for every n we have one identity matrix. This is I4. It's a 4 by 4 matrix. So 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. See that the main diagonal has one entries. All entries are 1s and the other entries are 0. Okay, what is the special property about the identity matrix is the following lemma. Let A be any matrix. Let A be an m by n matrix. So it has m rows and n columns. Then if you multiply A, notice that A has dimension m by n. So I need to multiply it by in, which has dimension n by n. So see, we get A. and if you multiply it from the right, and if you multiply it from the left, you need to multiply it by IM, the identity matrix of m by m, of dimension m by m, and here you multiply it by A. Okay, this has m by m, and this is a dimension m by n. So the main property of the identity matrix is that if you multiply it by any matrix from the right or from the left, you get the matrix you started with A. So if you want, the lemma is saying that this matrix, the identity matrix, is playing the role of the number 1 in multiplication. In the real numbers, when we multiply any number by 1, we get the same number, and in the matrices, if you multiply any matrix by the identity matrix, you get the same matrix. So the identity matrix is playing the role of 1 in multiplication. So exercise, prove it. Okay, prove what? Prove that if you multiply any matrix by the identity matrix, you get the same matrix. And here you need to use the definition of multiplication. Okay. And let me finish by this session by saying notation. Now if A is a matrix, so suppose A is a matrix, then if we raise A to the power 0, then by definition this is the, maybe it should be a n by n matrix. Okay, this is an n by n matrix. If you raise A to the power 0, then by definition we get the identity matrix. And in general, if the power is a positive integer, so A to the power k is defined to multiply A with itself k many times. And notice we can perform these multiplications because all of the matrices are of dimension n by n. Okay, so first you multiply A by A, and then you get A squared, and then to get A cubed. Okay, so A squared is A times A cubed is A squared times A, and A to the power 4 is A cubed times A, and so on. Okay, so try to multiply a matrix with itself. We can do this because A has dimension n by n and A has dimension n by n. So we can multiply the matrices to get a matrix denoted by A squared, which will have a dimension n by n as well.